My name is Laura Roberts, and I'm excited to present to you Watching the Watchers, nonce-based inverse surveillance to remotely detect monitoring. This is joint work with Dave Plonka, and we built this system while I was employed as an intern at Akamai. In today's internet, pervasive monitoring is deemed a threat. Internet users and service providers don't know who's watching their internet traffic. So we desire a way to detect who is monitoring internet traffic and where it's being monitored. We aim to answer the question, can we build a system that remotely detects monitoring? We propose the use of nonces to accomplish this. Nonces are single-use pseudo-random values. First, we actively disseminate nonces. That is, we transmit them as a packet's IPv6 source address in an active measurement survey. Then, we passively listen for a surveillant to propagate or react to the nonce. For example, to use it in a reverse DNS query. Because nonces are unique, we can correlate the dissemination with the subsequent propagations and reactions. And we're also able to glean topological information on paths that nonces traverse, which helps us locate where the surveillance might be. We present Noise, the Nonce Observatory for Inverse Surveillance of Eavesdroppers. Our agenda today is to describe the system and present our results. Let's describe the system. We disseminate nonces and listen for reactions. There is an active component to our system and a passive component. So we need a way to actively spread nonces, which we call dissemination, in internet traffic, and to passively detect reactions to these nonces, which we call propagation. There are various strategies we could use to realize both of these components, and we decided to use a worldwide IPv6 traceroute-like measurement campaign to do just that and detect surveillance. First, we generate 64-bit nonces, and because of IPv6's huge address space, we embed them in IPv6 addresses, which are 128 bits. And for example, we embed these nonces in the lower 64 bits. We generate nonces by encrypting 64 bits of data with the Cha-Cha-20 stream cipher. We do this because it's important that our nonces be unpredictable. If they were predictable, an adversary could craft and transmit valid nonces itself instead of merely reacting to ours, which would confuse our analysis. With our nonced IPv6 addresses in hand, we disseminate them by running a special traceroute campaign. In our special traceroute campaign, we craft or forge one-time use nonce-laden source addresses. We emit packets with those nonced addresses rather than the host's usual source address. And here in this diagram, we show one nonce per destination. And here we show that a reaction to nonce NY indicates that a surveillant was along the path to Y. However, we can go further than that. We can have a forged source IPv6 address for each TTL, or hop limit. The IPv6 number space is huge, so we can afford to place a unique nonce in every probe packet that we emit. This offers us finer granularity in determining where the surveillance actually was along the path. And here we show that a reaction to nonce NY2 indicates that a surveillant was within 2 hops along the path to target Y. In our experiments, we ran YARP on a computer dedicated to noise. This is our trace source host. We traced from nonced IPv6 source addresses to the approximately 15.2 million target addresses used in prior work, which is, to the best of our knowledge, the largest IPv6 topology survey to date. Notice that we are disseminating our nonces while getting a sense of the topology so we can know where the monitoring happened. Now, let's move on to the passive component of our strategy. After disseminating our nonces via this special YARP-based traceroute survey, we then wait to see who or what reacts with interest to our nonced source addresses. An example of interest could be the receipt of a packet destined for a nonce-laden address from a host that was not a target of our trace routes, and we capture all such unsolicited packets on our machine. And we call these PCAP reactions. We know from experience that a common reaction to unsolicited traffic from an unfamiliar address, in this case from our /36, is to perform a reverse DNS query on it. And we refer to these as RDNS reactions. And we have access to DNSDB, a passive DNS database, which allows us to determine when queries for nonced addresses or project domains were shared with this third-party commercial database. And we refer to these as PDNS reactions. So noise consists of all of these components, and more details can be found in our paper. Now let's discuss our results. Our results come from 3 experiments. In our experiment named UDP-443C, we used YARP to send UDP probes to port 443 of our 15.2 million targets. In experiment UDP-443S, we sent UDP probes from port 443 to our targets. And in our experiment named Ping, we sent ICMPv6 echo request probes to our targets. All in all, we transmitted over 1 billion nonces. So in this paper, we take a macroscopic and then a microscopic view of our results. Across 3 experiments, looking at this macroscopically, noise detected monitoring more than 200,000 times, ostensibly in 268 networks, for probes destined for 437 networks. Now recall that we are particularly interested in the following types of evidence and monitoring: RDNS, which represents reverse lookups; PCAP, which represents unexpected packets that talk back to our nonced source addresses; and PDNS, which represents entries in DNSDB, a commercial passive DNS database. So here's a table that shows the 3 experiments on the left, the 3 different reaction types, and the number of these that came from ASNs that were different than the target destinations, indicating that the surveillant was somewhere in the middle or was a third party. For example, here we see that for the first experiment, 43% of reverse DNS lookups came from ASNs that were not in the target destinations. Speaking of third parties, if we look only at RDNS reactions for experiment UDP-443C, we see the top ASNs that performed reverse lookups on our nonced addresses. We were somewhat surprised how common it is to use open public DNS resolvers, some of which you see here. This shows how data is being shared and propagated. Let's zoom in now for the microscopic view. Given the myriad instances of monitoring that we detected, we validated a subset of these by gathering ground truth for the capabilities we'll present next. Noise capability 1, detection of curious queries. In the top figure, you can see a visualization of 3 UDP-443C experiment traces to 3 separate targets that show evidence of monitoring. The horizontal axis is spatial by TTL, that is, the distance increases from left to right. The blue squares represent responsive hops. The green squares represent responsive hops that were in the target destination ASN of the trace. The small orange circles that represent RDNS indicate that a reverse lookup was performed on the nonce address of the probe we sent with that TTL. The bigger magenta circles that stand for PDNS indicate that we found the nonce address of the probe we sent having that TTL subsequently present in DNSDB. Finally, the big red circles that stand for PCAP detections indicate that a packet was unexpectedly received destined for the nonce address of the probe we sent having that TTL. The table on the bottom shows an abbreviated timeline of events that occurred in this experiment, and it corresponds with the top trace in the visualization. Notice that in the top trace, all of the squares are blue. This indicates that there were no responsive hops in the target network. A traditional trace route without nonces does not show whether the probes reached the destination network. However, we know that the reverse lookups that occurred on the probes sent to hops 9, 10, and 11 were performed by the target network. This demonstrates how Noise's modified YARP tool sometimes improves reachability measurements over those performed with either regular YARP or other traceroute tools. Noise capability 2, detection of sharing of passive DNS data. The table on the bottom shows an abbreviated timeline of events that occurred in experiment UDP 443S, and the bottom trace in the visualization shows a trace from experiment UDP 443C, but they both correspond to traces that were sent and had PDNS reactions by 2 universities. For example, in the table, we see that 18 days after our nonced probes were sent, we were able to detect a reverse lookup on the probe with TTL14 and its subsequent appearance in a passive DNS database. We spoke with expert operations personnel at both universities, and they confirmed that they were indeed using such a database. This demonstrates how Noise was able to pick up the sharing of DNS data with a third party. Noise capability 3, detection of eavesdropping. The table on the bottom shows an abbreviated timeline of events that occurred in this experiment, and it corresponds with the middle trace in the visualization. Notice that 3 reactions took place on the probe that was sent to hop 2, which is clearly in the middle and far away from the target destination. In particular, at around 10 minutes, a cloud provider sent 2 SYM packets to port 80 of the nonce address, and a cloud DNS provider performed a reverse lookup on the nonce address. Thus, Noise can detect some monitoring, can isolate its candidate location in the router level internet topology, and can ultimately show that information about traffic is being shared with third parties. Finally, let's zoom out again. Here's a bigger visualization of the type we showed earlier. We have all 3 experiments side by side with ASN divisions labeled on the right, and we can see how the different protocols affect the types of reactions we get from different networks. To conclude, we have presented Noise, the Nonce Observatory for Inverse Surveillance of Eavesdroppers, a novel way to detect monitors of internet traffic remotely. While Noise currently implements one mode of nonce dissemination, which we showed, many others are possible, for example, in the World Wide Web, and we envision a system that is so pervasive that surveillance would have no choice but to observe our nonce-laden traffic, improving detection of surveillance whenever they act on their observations.